I'm Terry Holbert from Ocosta High School, and we're going to do a lesson now on symmetry and graphs of circles. So here we have three basic types of symmetry of graphs. You can have an equation that is symmetric about the x-axis, and there is this simple test if it's symmetric about the x-axis. If you take the x and the y variable in an equation and keep the x variable the same but substitute in a negative y, and it comes out the same as the original equation, it is symmetric about the x-axis. And an example of an equation symmetric about the x-axis is x equals the absolute value of y, because anytime you have an ordered pair xy, you have a matching one x and the opposite y value. And you can see that this graph folds across the x-axis. Those two sides would fold right on the x-axis, and it's symmetric with the x-axis. Symmetry about the y-axis means the graph will fold over the y-axis, and on this one, if you take an ordered pair xy, it would map to the opposite of the x value, y. So that is the test to see if an equation is symmetric about the y-axis. And this equation happens to be graphed as y equals x squared, symmetric about the y-axis. And the last one we're going to talk about right now is symmetric about the origin. And a graph is symmetric about the origin if you have an xy value and it will have a corresponding one on the other side of the graph that's the opposite of the x value and the opposite of the y value. So that is the test for symmetry about the origin. And I tend to think about this as you could fold it over both the x and the y axis, because it has both the opposite x and the opposite of the y. So we're just going to start here with a basic line segment. Endpoints are at 1, 2, and 5. 1, 2, 3, 4, 5, 1, 2, 3. So here is the segment we're going to be looking at. So this is my original. It would ask you to sketch the reflection about the x-axis. So about the x-axis, the x value stays the same, but we're going to take the opposite of the y value. So instead of 1, 2, we're going to graph 1, negative 2. So this point would map down to that one. And then instead of 5, 3, we're going to go 5, negative 3. And that's what that segment would look like if it was reflected over the x-axis. So this is the answer to part A. Part B would like you to take that original one again, reflected over the y-axis this time. So this point would get reflected over to that point. And this one that's 5 away, 1, 2, 3, 4, 5, let's be 5 in the opposite direction. So instead of positive 1, positive 2, we're at negative 1, 2. And we're at negative 5, 3. So that is our solution to B, reflected over the y-axis. The last one here is reflected over the origin. And that's when you take the opposite of both the x and the y. So that we negative 1, negative 2, and negative 5, negative 3. So that's your answer to part C. Next. Here I have a graph of the equation x to the 4th minus 3x squared plus 1. And it wants to know what type of symmetry does this graph, if any, possess. And the graph appears to be symmetric with the y-axis. It looks like I could fold it right on the y-axis, and the two sides would match. So to test, to make sure it really is, we're going to use this test, xy mapping to opposite of xy. So we're going to take this, plug it into our original equation, so the y value stays y, but I'm going to put the opposite of x in for the x spots. So if I take a negative x times a negative x times a negative x times a negative x, that ends up being a positive x to the fourth. Here, if I take a negative x times a negative x, or the opposite, I'm going to end up with negative 3x squared plus 1. And then this equation is identical to our original one, so yes, it is symmetric with the y-axis. So substituting in a negative x for the x location gave us the same exact equation. So here's another one. We want to know what type of symmetry does this graph possess, if any. There's the equation and the graph of it on the calculator. And it appears to be symmetric with the x-axis. So we're going to use the symmetry with the x-axis test, which keeps the x value but puts in the opposite for y. So x would equal, I'm going to substitute in a negative y or opposite of y in the two y locations. So a negative y or opposite y, that would still be y squared. This would make it a positive 1/10 y minus 15. And if you notice, this is not exactly the same this time. Because this one has the one we have now is a positive 1/10 y, but the original one has a minus 1/10 y. So even though it appears to be symmetric, it's not symmetric with the x-axis. So we're going to try one more. This one, this graph, appears to be symmetric with the origin. So we're going to use our last symmetry test. We're going to put in the opposite of the x and the opposite of the y in the original equation. And then I'm going to simplify this out. So I have the opposite of y, negative x is going to be negative 2x cubed, and a positive 3x. Now you may look at that and say that that is not the same as our original equation. But I'm going to multiply everything in this equation by negative 1. So that would make that a positive y. We would have a positive 2x cubed and now a minus 3x. And that is exactly the same as the original graph. So yes, it is symmetric with the origin. So that's how you do the symmetry tests. This one, it's asking you to graph y equals negative x squared plus 5, but it wants you to complete the graph using symmetry. So we have some values to put in here for x. So if I put in 0, I will end up with 5. Be careful when you put a number in here. Then this means you're going to do the 1 squared and then make it negative. So we actually end up with a value of 4 there. And I'm going to put the 2 in place. So that's going to be 4, but that negative makes it a negative 4. Plus 5 is 1. And I'm going to put the 3 in. And I'm going to end up with negative 4. So 0, 5, 1, 2, 3, 4, 5, 1, 4, 2, 1, and 3 was 1, 2, 3, negative 4. So here is part of my graph. Now, if we look at the equation, if I substitute a negative x in for the x value, I do still get the same equation. So it is symmetric with the y-axis. So since it's symmetric with the y-axis, then I know this point, negative 1, 4, will still work. The point here will work because it's symmetric. And 1, 2, 3. And I can graph my equation. So you can use your symmetry rules to complete a graph that you're graphing by hand. Okay, so we're going to try that again. Here, we're going to take this equation, y equals -4 divided by x, and use our symmetry rules. Now, if it's symmetric with the x-axis, if I make the y negative, it will not be an equivalent equation. If I use my symmetry with the y-axis test and put a negative x in, it will not be the same as the original. But if I put in the opposite of x and the opposite of y, I would get, and then again, if I multiply both sides of that equation by -1, I would get the exact same equation that I started with. So that tells me it is symmetric with the origin. So I'm going to put the values in. So -4 divided by 0, that's not possible. So that tells me there is no value for when x is 0. If I put in 1, I'm going to get -4. If I put in 2, I'm going to get -2. If I put in 3, I'm going to get -1 1/3. Positive 4 would give you -1. And I decided to try 1/2. So -4 divided by 1/2, you have to invert multiply, actually gives you -8. And then -4 divided by 1/3, inverting and multiplying, gives me -12. So if I graph this, 1, 1, 2, 3, 4, -4 is there. So since it's symmetric with the origin, that tells me -1, 1, 2, 3, 4 will also work. And 2, -2, but also -2, +2. 3, -1 1/3 will map to -3, +1 1/3. 4, -1, and -4, +1. And then I threw in the 1/2, well, 1, 2, goes down, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, that is there. And then 4, 5, 6, 7, 8, and the 1/3, 12, even closer there, and up there. So this graph does not cross the x or the y-axis, but it is symmetric with the origin. So by graphing this branch, I was able to locate the other branch as well without having to substitute more values in. Okay. Next, since a circle is extremely symmetric object, we decided to talk a little bit about the equation of the circle as well in this section. So we have this distance formula that we've used before, that the distance is equal to the square root of the difference in your x value squared plus the difference in your y value squared. So here, if you think of a circle, all the points on the edge of a circle are the same distance away from the center. And that distance is the radius. So we can substitute r in for d in the equation, and our x2 and x1 values would be the x and the h. So the equation becomes r equals the square root of x minus h squared, and then our y2 and our y1 values in the distance formula are your y and your k. So y minus k squared. Or, if you square both sides of this equation, you get x minus h squared plus y minus k squared is equal to your radius squared, where hk is the center of your circle and r is your radius.